I'm Agustín Rayo. I'm the Associate Dean of Humanities, Arts, and Social Sciences. We have some fabulous speakers. They all gave me a sneak preview, so I'm very excited. What's going to happen is they're each going to speak for 10 minutes, and then at the end, we're going to have some time for discussion. And we'll proceed in alphabetical order. Our first speaker is Alberto Abadie, who's an economist. So he's an econometrician, and he is an empirical microeconomist. And he's a pioneer of synthetic controls, which is this important way of answering counterfactual questions in economics. So he's a professor in the economics department, and he's also associate director of our Institute of Data, Systems, and Society.
Okay, good morning, and thank you, Agustín, for the introduction. I'm not in computer science, and I'm an economist, but I'm going to use my time to talk about a recent confluence in methods and goals between computer science and the social sciences that, in my view, is making that our students in the social sciences know about computation increasingly important, but also that, computer science students know more about the social science aspects of the problems that they are studying. So reflective of this confluence that I'm going to talk about, like I guess many of you know, that at MIT we have now a new undergraduate major in computer science, economics, and data science. This is a very popular one. As Agustín said, I am faculty at the Department of Economics, and many of my students that I have undergraduate students come from this major. Also at the graduate level, our PhD students in economics and PhD students in political science now have the opportunity, they have the option of graduating with a dual degree in economics and data science, or a dual degree in political science and data science, and we offer that in collaboration with the MIT Statistics and Data Science Center. And this is also something that has generated a lot of interest, a lot of attention from our students. Aside from being at the Department of Economics, I'm also Associate Director of IDSS, that is MIT Institute for Data Systems and Society. The mission of IDSS is to combine expertise in information systems and the social and decision sciences to advance education and research, with the goal of addressing the most pressing, more challenging societal problems. And we try to do that using data and using analytical methods. And within IDSS, I guess I should be, there you go, that's what is this for. One of the programs that we have is the PhD program in social and economic system, and what we try to do there precisely is to train our students in the intersection between information system and the social sciences. Okay, so you can ask why all this assignment on the part of our students and on the part of the university to create this space of confluence between the social sciences and computer science. Well, from the previous speaker, I think this is pretty obvious. For once, the way we operate in social and economic environments has completely changed in the last 2 decades. Now we use automated systems and digital platforms to communicate with each other and buy goods and services, and to change our commuting route if there is traffic, right? And this is a quite drastic technological change and social change, but also one that may have profound implications for policy, and that's something that I, as a social science, care quite a lot about. And now we have both people in social science and in computer science that care about problems like electronic commerce, or algorithmic fairness, or the propagation of fake news in the digital platforms. Okay, and understanding these problems, if we want to understand these problems, we need data, we need models of human behavior, but we also need an understanding of how the system works. Okay, so this confluence of goals also has created a confluence of methods. Like if I tell you that I'm teaching a course on about complex dynamic systems and networks, or causal inference and prediction, call it machine learning, and game theory, mechanism design, or artificial intelligence and dynamic discrete choice methods. Like perhaps you don't know if I'm doing this in the Department of Economics, or I'm doing this like in a Department of Politics, or a Department of Computer Science. Okay, so this confluence of methods also is facilitating not only the communication across fields, but also teaching across fields. That's something that we try to do here. Another tectonic force that is reshaping the social sciences and is reshaping what our students should know is the changing the nature of the data. I'm an economist, data is one of the primary ingredients of of science, and in the past we used data that came from experimental sources, survey sources, administrated sources. Okay, and these data sets tend to be very granular in terms of they describe the individuals in the sample very well, but they tend to have very limited information about how these individuals interact with each other. Okay, and because of that, people in the social sciences are more and more interested in what we sometimes call big data sources. Okay, and then for often in computer science, people will think, okay, so what is this data? What is big data? Big data is data that is big. And then, for me as a social scientist, that characterization is not particularly, appealing. But we may think about big data in different ways. We may think I like to think about the big data as a data environment that has three components. First is a vast quantity of data that are collected routinely by automated systems. Okay. Second is large computing capabilities allow us to analyze this data in real time. And third is we can use this same automated system that collected data to deploy sophisticated personalized intervention. Okay, so for me as as an economist, when I see this a new big data environment, what I think it is what is going to reshape the social sciences in the next couple of decades is how to use these large amounts of data, how to use these large computing capabilities to make public policy more efficient, smarter, and to address complex societal challenges that we have. And that is what we have to train our students for. I think that as it was said in the previous intervention, in the previous talk, our students are going to be in this heavy interdisciplinary environments, and we need to provide them with the tools and the methods that they should have in order to be able to successfully address these type of questions. Okay. And thank you very much.
Thank you. So our next speaker is Mike Cuthbert, who is an expert in computer-aided musical analysis. So he is the creator of Music 21, which is a very broadly used toolkit for computer-based musical analysis. Mike is a professor in the music department, and he's also faculty director of digital humanities at MIT.
Thank you all for coming. So I'll not wear my music hat today, I'll wear my humanities hat, and just say a little bit about humanists. Humanists are people who tell stories about the world. And that's about our world, the past, the present, occasionally the future, but you know. And we sometimes couch our writing of stories in language that says, you know, something like, well, we construct new narratives that invert perpetuated hierarchies of privilege, but really, we write stories. And it's another way of saying that I'm writing a new story, a different story, hopefully a better one, but at the heart, a story. Now, sometimes our stories are about really big things, the French Revolution, the structure of families in Africa. What does a Sistine Chapel really mean? And quite often, though, they're about very small things that we hope to lead to something bigger. In my training as a music historian, I once wrote 40 pages on one sheet of music paper. It happened to be blank. A blank sheet, yet from that, you know, I was able to get into the structure of economies of monks in Padua and Italian foreign relations in the 15th century, and so on. But whatever it is, it's a story. Now, what distinguishes us from screenwriters and novelists whom we hope write better stories than we do, is that our stories need to be about this world, about facts, real events, at least as much as we can discern them, and stories that are based on evidence that we discovered, analyses that we conducted, and stories that could not have been told before. In this research process, which we might call data gathering, good humanists behave kind of like the scientists and engineers we're talking about. And when I say that stories are the essence of the humanities project, of course all researchers create stories. But to the extent that the story, the narrative, is fundamental to the project, I think is what connects disciplines to the humanities. It is why at MIT, the undergraduates learn to write in the humanities first before taking writing and speaking classes in their own disciplines. What also unites the humanities with the sciences, engineering, and the arts is love of experimenting with the new, and that includes new digital technologies. There are a lot of us tech nerds in the humanities, and not just here at MIT. There's also a great yearning in the humanities for ways to use technology to make us better researchers and better teachers. But computers and the humanities are not always an easy fit because of all the amazing, brilliant, spectacular things that computers do. Telling stories is not one of them, or at least not today. Retrieving information, finding patterns, identifying outliers, these are the tasks that right now our computers are great at doing. But asking how come is not something that comes naturally to our Siris and Alexas and Googles and Bings. And I kind of reminds me, those of us of a certain age can remember our friends firing up Netscape and typing, why is it that ... into Alta Vista before they learned, like the rest of us, that if you just stick to the nouns, you're going to get a much better result. So how to go from data gathering, machine learning, and analysis to writing stories that answer the questions of why and how is not at all obvious. It's something that needs to be learned. And if something needs to be learned, it's something that needs to be taught. Earlier this year, we started at MIT a major set of projects related to connecting programming and emerging digital technologies with research and teaching in the humanities. The programs in digital humanities at MIT launched last September with a mission to use code to encourage communication across the humanities CS tech world divide and build a community of practitioners fluent in both languages. We wanted to assemble and train a group of people who understood how to write code and employ algorithms to help understand the questions about the world that the humanists already had. And equally importantly, to how to read data to come up with questions and narratives that we didn't know were important before computational analysis. Our aim over the next 3 years is to have our work affect the humanities faculty, the graduate students, Boston, and the world. But you have to start somewhere. And what we thought about starting with was, what's a group of people who are incredibly smart, incredibly motivated, but too naive to know that everyone else has said this is too hard? So we started with freshmen. The lab projects in DH this year have brought together 30 undergraduates, almost all first years, to think about problems in literature and history that have too much information for one researcher to keep in her or his head at one time. So the first project we threw our students at was looking as much and learning as much as we can through computational methods about gender relations in 19th century novels. So we tasked the students, build the first major corpus focused solely on novels that were originally written in English in the 19th century, assemble all the necessary metadata to classify them, apply gender classifiers to characters, look at clusters of pronouns, connections of certain words, primarily with people of one gender or the other, apply grammar parsing tools, and read as much literature from the humanities about the topic as you can. Also, build a website, learn to code in standards in teams, peer review each other's code, learn Git web frameworks. For many, learn Python for the first time, Z3950 queries, accessibility standards. And let's analyze some Jane Austen by hand, just so we learn how to do that. And do all this while taking intro CS, calculus, physics, writing class biology, and since we're talking about freshmen, learn to do your own laundry. We gave them 2 months, and they did it. Together with my amazing postdocs, Lisa Taliaferri and Stefan Risi, they assembled a repository of 4,200 novels from the American Revolution to the end of the public domain, 327 million words in all, and analyzed it. In making our project, research and teaching are intertwined. Classes and workshops on technical, computer science, and literary topics led directly to new discoveries. One lesson we learned was that as much as we all loved playing with the latest machine learning classifiers and other cutting-edge technologies, the field of digital humanities and connected to computers is so wide open that often the simplest programming techniques were still able to come up with the most interesting and the most compelling results. And I want to talk about one of them just very briefly. After all this work on classifying gender and stuff, we said, well, let's just count pronouns, and let's look at how pronouns are connected to each other. And one of the things that reinforced sort of something that we already thought we knew was that male authors much more often talk about men, and female authors talk about men and women about equally. Now, that's something that I think will not come as too much of a surprise. But once we looked at where in the sentence do female and male characters appear, are they subject pronouns, he or she, or are they object pronouns, him or her? The female and male authors had almost exactly the same usage, but men are being put in the subject position, doing something to, and women are being put in the object position more often. So this is sort of an idea of some of the work that we're working on. I'm looking at the time, so I'll skip over one slide. So one of the qualities of the DH lab that has really created great results is the diversity of the lab. 3/4 of the members of the lab are women, and 1/4 are members of underrepresented minority groups. And by the way, we did not announce what the project we were going to be working on before the members signed up. So to build a more diverse CS world, bring more humanities applications to the table. I want to end by saying what we're doing now because it's relevant to all of us who are here building the Schwarzman College. In partnership with the libraries, we're digitizing, analyzing, and text mining and making public thousands of documents relating to the founding of the Computation Center at MIT in the 1950s. We hope that by looking at how it was founded, what opportunities were seized, we can duplicate and replicate that today. And when we look at what mistakes were made, we can avoid them in the future. The future of humanities depends on our ability to bring in computational resources. And I think the future of computation's ability to affect positive societal change depends on bringing the humanities to the table. I think both futures at MIT are very bright. So thank you.
Our next speaker is Erik Demaine, who's a mathematician. You may have heard of him because of his work on the mathematics of origami. He is the only mathematician I know of who has work in the permanent collection of the MoMA in New York and the Smithsonian Institution in Washington. He's a professor of computer science and electrical engineering at MIT.
Thanks. We're here to talk about interactions between art and education, and I want to throw a third circle into the Venn diagram, which is research. And I think a lot of, this is why we're here at MIT, is to do all three of these things. Maybe you don't think of the red one, but that's the topic today. And I think there's a lot of really exciting things we can do at the intersection between these three. And let me talk about the intersection between art and research. I think I do a lot of work at that boundary, and I think it's a really fun way to work, that by doing art, we get inspired to do new research, and by doing research, we get inspired to do new art. And I'll give you some examples of that through origami and glassblowing. And on the education side and research, I think we should be doing more research in our educational setting, like we just heard in that freshman seminar. It sounds like a great research endeavor. Unsolved problems are fun and exciting, and they're why we're here, and I think it's a great way to motivate students to learn stuff. I've written over 50 papers from classes and with students in those classes, and I think it's a great way to teach students to collaborate as well. So, let me tell you a little bit about origami. This is a field that started as essentially an art form and now has lots of practical applications on the science side and lots of interesting mathematics and computer science. Every advanced origami artist has to learn the mathematics and the geometry of how to lay out parts of the paper to make their desired form. This is an example by Jason Koo, who as a high school student designed this hyper-accurate butterfly by learning mathematical theory for how to do that. He wasn't a mathematician at the time, although he then became an MIT student, and now he teaches computer science at MIT. And so that's an exciting application of computer science to art. And a more recent example of a technique for this we call Origamizer. This is just finished last year, and the input to this algorithm is an arbitrary 3D model like the bunny in the top left. The output is a crease pattern like that thing in the bottom left. It takes about 10 hours to fold, but it uses almost a quarter of the material of that square of paper and folds into exactly the 3D model you asked for. And in particular, this algorithm comes up with crease patterns or designs that no human could come up with. And so this opens up a whole new world of possibilities for origami art. And so that's exciting. But there's also lots of applications. Let's go to education. This is a class I teach at MIT called 6849. And you see the kind of spirit going from the top of a conceptual design. I want to make my logo. An algorithm turns that into a crease pattern, and then you fold it by hand into that 3D model. An exciting thing for me about this class is it's taken by a lot of design students from Department of Architecture, and they're just excited about what kinds of geometric designs are possible with these types of algorithms. So we have found a way to teach what's ostensibly a mathematics and algorithms class to design students in addition to the regular computer science math students. So that's a lot of fun. There's also lots of practical applications for origami. This is an example led by Daniela Rus, who's here, and a collaboration with Harvard and Penn to make robots out of flat material. And origami provides a way to do that 2D to 3D transformation. And so the result is with $10 or $20 worth of materials and a laser cutter, you can make a custom robot in just a few hours. So that's a really exciting, I'm going the wrong way, sorry. That's an exciting thing. In particular for education, you can imagine in a robotics class, everyone gets to make their own custom robot instead of using off-the-shelf robots. Even in a grade school setting. This could be really fun. Still lots of work to do. And one example I wanted to show is pleat folding. This is something we've been working on for about 20 years, and we've gone back and forth between the science and the art of pleat folding. The story begins in the 1920s, when I was very young. This is the Bauhaus in the late 1920s. Joseph Albers had this design class where some student folded these models. We don't know exactly who. And it's a brilliant idea. And he was using paper folding as a way to explore design without worrying too much about material and constructability and being able to prototype really quickly. So we explored that idea, and these are the pieces mentioned in MoMA and the Renwick Gallery at Smithsonian. And so what really excited us here is we didn't understand the mathematics of curved crease folding. We didn't understand the research side, so we were stuck. We just switched gears and entered the art side. And while my background is in computer science and math, my dad's background, my dad is over here, his background is in visual arts. And when I started working in geometry, he got excited and said, oh, I see a kind of symmetry between solving research problems and solving art problems. And that's, so then we started working together. And I keep auto-advancing here. And so I taught him to become a mathematician, and then he taught me to become an artist. And so now when we get stuck on a math problem, we can switch over and do art instead and get unstuck. And as a result of that exploration on the art side, we were able to characterize how curved crease folding, at least to a large extent, works mathematically. So over the last few years, we have better and better understanding of this, which is really exciting. And a nice example of how we can be more productive going back and forth between these two worlds. I'll show you one more example, which is in the world of glassblowing. My dad and I are also glassblowers. He was actually the father of glassblowing in Canada, also father of me. This is an example of a beautiful glass piece made here at the MIT Glass Lab by Lino Tagliapietra during a visit. He's the world's best glassblower. And for his color patterns, he uses this idea called glass cane. And there's a set of traditional glass cane designs which are shown on the right. And they are, for centuries, they've been the only patterns out there. And so on the research side, we were curious, can we do other patterns? And so we came up with this software and used it to design new glass cane patterns. And then we make them out of glass, and they look cool, so success. But this project has been even more successful than we imagined, because the software we published, it's called Virtual Glass, you can download it and play with it, it's free, is now used on the education side to teach glassblowers how to blow glass. It is still the only software for computer-aided design of glassblowing, and so artists use it to sort of pre-visualize what pieces they're going to make, and educators use it to teach how glassblowing works. And so the point is, at this intersection between art, education, and research, you get a lot of really exciting things. You might be initially inspired, in that case, by research, or designing new art. It's somewhere at that intersection, and have accidental implications on education. And if you're comfortable bouncing between all of these circles, I think you get stuck a lot less. If you have a hard time solving a math problem, you can make a sculpture about it. Or you could share it with your students and say, hey, look, here's a cool open problem, let's work on it. If you get stuck making a sculpture, making sculptures are hard, sometimes they're impossible, and you can prove it, that leads to new research problems. And so I think this is an exciting space to play in, and happy to be in this panel. Thanks.
Our next speaker is Eran Egozy, who is a mathematician, entrepreneur, and technologist. So he's a co-founder of Harmonix Music Systems, which makes real-time music-generating computer programs. So famously, Guitar Hero and Rock Band. And he's a professor of the practice in our music department.
Thanks, Agustín. I'm actually going to switch over to my computer for a reason that you'll see soon. Can we switch over? All right. So I was thinking about how I teach music. I'm in the music department. But I'm a music technologist, so I was thinking, well, I teach computing with music, but maybe I could also title this talk Teaching Music with Computing, because at least I think of it as two sides of the same coin. I teach a class called Interactive Music Systems. It was the class I designed after finishing my stint at Harmonix with Guitar Hero and Rock Band and all that stuff, and trying to sort of synthesize everything I learned there in industry and figure out how to teach it. And I was sort of thinking of, well, okay, I want to teach computation. I actually want these kids to learn how to program well. You know, I learned a lot of how to program at MIT, but there's something about the practical experience that I wanted to share. So I cover topics like data abstraction, encapsulation, real-time systems, HCI, and especially code quality, but it's all applied to music. So we talk about music and music modeling and sound synthesis, and actually get into how do you mathematically model composition or performance or music theory. And of course, it's all wrapped up in music, which is an art form. But there's a lot of design elements as well. So art and design, there's kind of an interesting interplay there along with computation. We talk about aesthetics and interaction design and style and that kind of thing. And so I want to show you an example. About, I don't know, third into the course, I have an example I point out, which is, let's build a metronome. Does everyone know what a metronome is? Yeah, hopefully you know that annoying thing that is always off, like you play and it seems to never tick at the right. Well, that tells you need to practice some more. Okay, so, oh look, it's code. I have a class called Metronome. I thought since this was a conference on computing, I should actually have some computing. So this is some code here. If you don't know Python, that's okay. This should all still be fairly clear. So what happens here? I have in the beginnings of a class of a metronome, and I have a function called onBeat. When I call that function, oh, it plays a tick sound. Okay, so that's great. So I have a beginning of that, but it's I need more than that, right? In fact, one of the things we learned about is function pointers and callbacks, and how do you do scheduling with computation. Well, you can see this function here called onBeat. It sets up some parameters and calls play note. That's that tick that you heard. But I actually want this thing to play more than one note, not at the same time, but at some point later. So I have a scheduling function, which I will call schedule. And I want to schedule this function onBeat, okay? Oh, self.onBeat. When do I want this to happen? Well, not now, but later. Okay, later. Well, what is later? Later is now. Now is the tick. Now, in computational music, what we sometimes do is divide beats into subunits. Much like you divide a minute into seconds, we divide a beat into ticks. In this particular case, I'm saying that one beat is 480 ticks. Okay? So I have the tick, which is now, plus I have set up my beat length here, which is exactly 480, so it's one beat later. Okay, and that's later. So let's see if that works. Aha! Okay, so the function is being called and then telling itself to call itself over again. The wonderful thing about scheduling when you're in the musical context is that we have this thing called a tempo. A tempo is simply a mapping between tick and time. And so I can raise the tempo and increase the speed of that or slow it down. Okay, great. So we have a metronome. And that's fine, but we can probably do more than just a metronome, right? In fact, what I want to do is take this whole thing, and normally I do not recommend cut and paste coding, but I'm going to do it anyway because I'm kind of lacking time here. And let's create a new kind of thing here, which I will call not a metronome, but the lead line, okay? So I'm actually about to create an instrument, a virtual instrument. I don't want it to sound like a metronome, so I want it to sound more like, oh, I don't know, a saxophone, which I happen to know is 65, okay? And let's just see what happens if I play it. Oh, in order to hook it up, I need to actually create one, so I'm instantiating the lead line. Okay, it's a lead instrument, not a load, a lead instrument, and it's going to be on channel 1 because I want it to be independent of what I heard from the metronome, and I will also create it here. Okay, so that lets me set this up. Okay, now, some of you might consider this music. There are minimalists around us who might perfectly like this, but let's see if we can do something a little more interesting with this lead line that we just created. For example, the pitch. The pitch is marked at 60 right now, which I happen to know is middle C. So what you're hearing is middle C over and over again, but let's make those notes a little different. Now, if I have to choose some notes, I often rely on this really kind of dirty trick, which is random. Okay, so randint is a really handy function which returns a set of integers. I don't know, from say -12 to 12. Okay, so I'm just adding a random number, and so who considers this music? A few people. Okay, that's all right. Now, again, depending on your sensibilities, you might like that or not. You might want this to play a little faster. Like, for example, I can have it playing like that. Or maybe it might be interesting to change the pitches a little bit. So here we're starting to think about how we actually apply the rules of music to computation. Okay, so instead of random int, which is a little too random, I will use random choice. And random choice will let me pick from a particular array of values. Those values I think should be 0, which is the root, and then 4, which is the major third, 7, which is the perfect fifth, and maybe the octave, which is 12. Okay, so we got something that sounds a little more reasonable, or I could even go harmonic blues. Should we do that? 3, change the 4 to 3, now we're in minor. Add a little bit of a flat fifth, that's that blues note. Maybe add the minor 7th. Right, so we got kind of a bluesy thing going here. That's kind of cool. And also, you know what? When people play music, they tend to not just play the same note over and over again, right, as eighth notes or quarter notes, but they kind of vary it up. They kind of mix it around. So maybe they do this. Okay, so are we getting somewhere? I think we are. I have another thing here, which I call the bass. Okay, and I will just bring this up over here just to save ourselves a little bit of time. The bass is a similar kind of instrument, but it moves a little bit more slowly. Let me just hook the bass in right here. Bass and bass. Okay, and let's connect it. Oh, no, it should be 2, not 1. And one of the wonderful things about coding in front of your class is it keeps you really honest. Also, if you write any bugs, they are right there to tell you, oh, you have a bug over there. So now I have a bass. Okay, so now I'm actually making a piece. I'm like, in about, I don't know, about 5 minutes, I've been able to construct a piece of music. The only thing that's missing, well, there's a lot missing, but one of the things that's kind of interesting here is the 60. Remember that 60? It's middle C. Well, why does that have to be fixed? It could be a variable, which I will call G root. I'm calling it G because it's a global variable. I know that's bad. Okay, I know. Okay, and I set that to 60, which means I can change it. I have some keys hooked up to change that value. So. So in my class, the way I've decided to teach computation in music is to do it like this, essentially to show that computation is exciting. And there's a reason to do it because you can create real-time systems. And as you are learning about computation, you are also learning about music and the rules of music, and they all kind of interplay around each other. When I have my students work on projects, they always do things in 2 steps. The first is they build a system, they build technology, they use their engineering skills to actually build some tech. And then the second thing they do, because I asked them to do it, is turn that tech that you built into something creative. And I just wanted to show you a couple of examples of what that looks like. One of the things that they like to build is using this device. It's a leap motion. I don't know if you've seen it before, but it essentially allows you to use your hand as an interface, a spatial interface. Great, okay? So one of the tasks is, actually this is problem set 5, P set 5, build a harp. Okay, so this is kind of what it looks like, and you learn about graphics, but the creative part is where it really gets interesting, and I ask students to build different kinds of harps. Well, why do harps necessarily have to have strings that are all exactly the same length? Or how about a harp that can, I don't know, change the modality as it happens? Or what about a harp, I love this one. This was around Halloween. Right, I love the tonalities that the student picked in order to create this spider harp, or something that I also found quite soothing, sort of a three-dimensional kind of rising sun. Sorry about the glitching here, but. Okay, so you give students the opportunity to build something, but then also use it in a creative way, and you get amazing results. So, thank you.
So I'm sure you can all see why Eran's class is basically the most oversubscribed class in the school. Our next speaker is Éva Tardos, who's a mathematician. She's best known for her work on network flow algorithms and for quantifying the efficiency of selfish routing. And she's a professor of computer science at Cornell.
Sorry, that's quicker. Okay, thank you very much. And maybe this previous talk was exciting, showing more projects than I will be able to show. I want to talk to you about a very oversubscribed class at Cornell called Networks. It's a course that we have been offering for 10 plus years and it's been taken by 600 to 700 students per time we are offering it. Cornell has very few large lectures hosts of this sort, but we have secured one of them. It's cross-listed with economics, sociology, and information science, and computer science. And there's a really wide range of students taking it. Maybe I'll come back at the end of who the students are, but I want to tell you a little bit about what the course is. What the message is, what I want to get across in the course is want them to see network effects all around us. And I think I don't have to convince you all that there are network effects in everything we live in, that when someone does something far away, that somehow indirectly affects a lot of other people around. But students tend not to see this, and the goal of the course is to have them walk away seeing the network effects around in their everyday life. Tools, the mathematical tools are graph theory and game theory is what we basically tool them, and I said I'm a mathematician, so this is a pretty mathematical course. But we go from applications in various different places, from markets, for contagion, for small word phenomena, and lots of other things. What I want them to go away with is how the world is a connected place, how things stay connected online, how rumors propagate, how facts propagate, how markets are affected, and a bunch of other topics. I will give you a couple examples of what are the topics we're covering, but maybe want to start with what is, I think, our best tool to achieve what I want. That is, I want the students to see the world around them as a place where this is happening. Part of the course project is the students writing mini essays, which actually 2 of the mini essays are in a form of a blog post. And I gave you a pointer here to our blog, which you can check out. This is pointing to the current run of the course, that is the 2018 fall incarnation. What they have to do is twice in a semester, they have to write a blog post about something that we didn't cover in the class. So they're not allowed to mention a topic that we did cover in the class. They have to mention a topic we haven't not covered in class. But it has to mathematically connect to something that we did cover in class. And the way we do this as a blog post is ask somehow a random ordering of the alphabet based on the first letter of your last name. We give you a week, that on this week you have to post a blog post, and you get some credit for this blog post if it's indeed connects to something in the class. If it is something that happened in the Word out there, maybe you're supposed to give us a pointer in the news or a pointer to a company, and it's rolling over the semester. There are some unlucky guys whose last name starts with the wrong letter and they are the first to write. But they can, take inspiration from last semester's run. And the other people can read the previous blog post. We certainly get a culture where people do read each other's blog posts. I don't mean all 700 of them. Only our TAs have to read all 700 of them. But they read each other's blog posts, and I learn an insane amount about the Word by reading these blog posts. They name companies, they name products, they name all kinds of things that are really, really interesting. And I think this blog post, more than any of the topics we cover, is what gets them to, oh yeah, it's all around. It's everywhere. I think it's very, very successful. Typical topics coming from the news, can come from the technology world, and actually they're allowed to come from their personal life, though the first two are probably more common. So a couple examples of pictures we're using. We definitely use a lot of Facebook in introducing graphs and networks and talking about how do you discover how do you discover structures and friendship structures and what people's friendship structures are like. So one topic is some of them explore their own neighborhood, and does it have the same sort of pattern? We certainly talk about the web page and search among webs and how structure of web pages is connected. We do talk a lot about spreading rumors or spreading things on a network, whether it's rumors or anything else, technology. We do talk about the market and effect of technology, and both in terms of abstract models and also in terms of very concrete, who's in good position in networks. We talk about something that was mentioned as something that's closer to my field, is how strategic interaction of people can have a surprising effect. What I have in the bottom here is what's called the Brace paradox. It's a paradox where if drivers go through a network and I'm going in the wrong direction again. I don't know. Oh, thank you. But I missed it. That's okay. I can tell you in words what the Brace paradox effect is, that you can, I see, I can go forward. Brace paradox effect is that sometimes in a network, if everyone naturally chooses the shortest path on a network, one intuition would suggest that, hey, they're optimizing their routing, they're doing a good job going as fast as they can. And if you put in an extra link in the middle, then this selfish optimization will turn into a disaster. And while without the link it was shorter, with the link, selfish optimization will lead them to route themselves in the wrong way and have an extra, in this example, 25 minutes extra to the routing. At the end of the course, virtually all the students see the strategic interactions around them. They see the strategic interaction in our everyday political life. Like, again, a lot of the blog posts are about the current politics, like, what's happening between Trump and the Congress, and what's the game theory describing this. They see the game theory around the everyday interaction with their friends, and they see the network and connectedness and effects, and I think this is something they take home whatever level they are. So here is a little summary I promised in the beginning. So Cornell has 7 colleges. So the 3 biggest one are engineering, arts and sciences, actually other way around. Arts and sciences, engineering, and College of Agriculture and Life Sciences, but we also have smaller colleges. Every college has students that are sending to our courses. Here is a beginning distribution of what the students are, and I do admit the biggest enrollment is from the engineering college. Of the 700, 276 last year were from engineering. But a lot of them are from the Arts and Science College. There are a lot of them from the College of Agriculture and Life Sciences, and also from the smaller colleges proportionately. With this many engineering students, it's very important that we don't make it too mathematical. I want this message of the world is a connected place and strategic interactions are affecting all of us is something that every student can benefit from, whether you're a psychologist, a political scientist, or any other form of scientist, or not even a humanist. And indeed, we have enrollment from all kinds of students. The vast majority of the students are either freshmen or sophomores, and they are unaffiliated, that is, they do not yet have a major. But those that do have a major range from psychology, political science, and yes, of the engineering fields. To make this very diverse audience be able to live together in a single course, we use an absolute grading scheme. If you do the homeworks and do the blog post, you can get an A. And it doesn't matter how many mathematically inclined students are there who can do some of these things better. You can get your A or get B or whatever grade you deserved in an absolute scheme that makes students much more comfortable. And indeed, some of the projects are really cool and involve coding, and some student explore their own Facebook friendship page and do all kinds of interesting statistics out of it, and clearly that person knew how to code, knew how to download the web page, and knew to do more interesting statistics. And other students do something that's more at the abstract level about news, but the course has been very popular, and a lot of students after the fact report that this was one of their favorite courses at Cornell. So thank you.
All right, so we have 15 minutes for questions, and what I'm going to do is I'm going to start by asking a question to our panelists, and then I'll open it up. So my question is, suppose you're in an elevator with an undergraduate, and they ask you, how should I go about integrating my STEM training with my training in humanities, arts, social sciences? What's your elevator pitch? Any order you want. All right, Alberto.
Okay, could you put a little more structure in the question? How you integrate in which ways?
Yes, the student in question is at MIT. Mm-hmm. They want to be a computer scientist, mm-hmm. and they start out skeptical of
about things like social science. Okay, so I think in fact it's a quite easy many students that come to my class in statistics in economics and the social sciences, they come after taking many courses in computer science, and they kind of see there is a new world in which using data to solve social problems and to approach things that they care about. All these a type of examples that we were talking about, like how people connect in Facebook, the dynamics of traffic congestions and so on, and different people have a different type of inclinations in what they care about, the things that they want to do for in their professional life or in their academic lives, and it's really easy to see how this connection between what they are already doing many times in computer science and what we have to offer in the social science connect. And give them extra leverage to approach all these problems. So I don't know if this is an answer, but my answer is it is really easy And it's not only that. This not only comes from us, comes from the students. They are demanding this type of education. So I don't think that we have to convince anybody to do that. They come to us already convinced in this way.
I like it. Yes, Eva.
So as only non-MIT faculty here, I want to put in a pitch for, of course, in some way, this is easier at Cornell. A lot of the students, I do admit technically oriented engineering students. Often, if they admitted to MIT, they choose MIT. But the ones that do not do this, I don't do it because they take them by wanting to have a full-fledged university with the social sciences and the humanities around. So we do have a lot of students who are really, really interested in this integration. And actually, I downloaded the major distribution from my course before I was speaking, and a couple of kids were interesting double majors, like English and computer science double major, or psychology and computer science double major. So with this said, there are students who need a little bit of convincing, and because Cornell is a full-fledged university, we actually do have requirements that they take some other courses. But one advantage I have is I tell them to talk to their friends. I can tell them about interesting courses that a lot of people liked, that have nice connections. And we do have faculty at Cornell who are connecting computing and the social sciences and computing and humanities. So they can even take courses in the computing part of Cornell that connect, which usually then encourages them to take courses as well. After they take computational linguistics, they tend to want to take the real linguistics. After they take computational humanities, they want to maybe take some humanity courses.
Well, since we have a lot of people here who are visiting from outside of MIT, I just want to say that MIT does require all the students to take a quarter of their courses in humanities, arts, and social sciences. And because one of the things that comes out of this, the students quite often, they're in these classes, they're immediately, when they're assigned professional literature, scholarly journals, they just say, wait, I don't understand this part that says, well, we can't ever estimate, how many, how many pieces of medieval art were lost on the basis. And they go, well, of course you just do the Poisson distribution. And what the students really just need is the encouragement of the confidence that they have skills in connecting the humanities and technical science and engineering that others don't have, and that just to go ahead and do it, and sometimes go ahead and do it even though you don't know what question you're pursuing, and sometimes the questions will come out of that. I had a student who really, this is about 10 years ago when 3D printers were really, really new thing, just wanted to print Renaissance musical type. And I was like, well, I'm not sure what you're going to learn from that except how to use a 3D printer, things, but heck, let's do it. And she bribed me. She said she would give me copies after it was printed. And by doing so, just holding this tangible object, we learned so much about things that I thought I knew about how printing worked at the time that I didn't. So just, I guess the elevator's already got off, so just do it. Do it.
I guess the one thing I'll say is, and this is kind of based on my experience when I was here, 25 years ago. I mean, back then it was actually more difficult to combine CS with other disciplines. And I looked around at MIT for a while, and I played clarinet, and I did tons of music and then tons of engineering, computer science, and they were essentially separate. And it doesn't have to be that way anymore. And I certainly tell students that, and I think they kind of know that, and MIT is definitely going more and more into that direction, which is really exciting. But the main thing that I encourage them is to just think about not what they think they should be doing, but what their passion is and what they actually want to be doing. Because I think we all have this secret thing that we actually know we love to do, and for some of us, we think that's not possible in the world because the thing that I want to do is weird, or no one will pay me to do it, or that kind of thing. Certainly that's the advice we get from our parents. Well, you have to go into computer science so that you can earn a lot of money, And the thing is, like we've seen in what's happening in the world today, where everything is getting interconnected. and how all these disciplines are related to each other. Really, I think no matter what seemingly obscure thing you think you love, there is going to be a place for it in the world. And so you should pursue that.
Erik, do you want to tackle the elevator challenge?
Sure. I mean, in computer science, what I most often encounter are the computer science graduate students who are closet artists, and they don't share that with anyone because they don't know that it's okay. And I think the biggest thing is just to tell them that it's okay. And often it's like, oh, how can I fit this into my reward structure? And I tell them, oh, you know, there's these publication venues where you can talk about your art, or you could exhibit it, and that's like a paper. And so just sort of fitting, I think in general, crossing over these boundaries, you need to explain what the other side is like. Because people are typically only brought up in one silo, and so they understand the reward structure within that silo, and you just need to translate across that boundary.
Excellent. So we now have a few minutes for questions from the audience, and I believe there are microphones. No. Oh, yes, there are microphones. So if you want to ask a question, raise your hand or stand up, and a microphone will come to you.
A question for Erik. So is there now a robot that will do the folding for you, so you don't have to even do that?
In robotic folding, the main place where we've had success is in building sheets of material that fold themselves into the robot or 3D structure. And it's possible, but it's also difficult. There's still a lot of problems to work out. The bunny was folded by hand, yeah.
This is an open question. I think there's a lot of excitement about what computing and computer science can bring to other disciplines and what new insights can come from using computational methodologies. And I'm wondering about the other direction. You kind of touched upon that, especially Erik. In some fields it's not as clear. For instance, in humanities, what can computer science and engineering gain from being exposed to humanities scholarship, skills, methodologies, and so on? Thanks.
One of the main things that I think computer science students can really learn from the humanities is that a lot of what we're doing is working with data where you have to come up with that balance between generalized algorithms that work very well on everything and domain-specific knowledge. And I think that working through humanities problems or arts problems can really be a place to figure out where the boundary between how much domain-specific knowledge should come in. And the answer is almost almost never zero, but it's also almost never everything. And so trying to figure that out is something I feel like my students have learned the most.
And at MIT, there's a big focus on problem sets, which tend to have this very clearly specified problem, and there's a very clear answer you're trying to get to. And I think humanities offers this, and arts offer this way to think about problems that maybe aren't so clearly specified, and how to translate unclear problems into clear subproblems. I think that's a really good motivator for that kind of creative problem posing, not just problem solving.
Right, and we're seeing now areas where CS or computation is actually creating art, you know, and so I think that leads to a really interesting question, which so far we haven't really had to answer as computer scientists, which is it good art? You know, like how do you judge something that is fundamentally not really supposed? It's about taste, you know. So we have computers that create artwork, or computers that create music. Is that music good? And so I think that's an interesting question that we're only able to start asking right now.
So I guess one place that maybe is not quite what you asked is humanities, but social sciences. I mean, we are living in a world, and social sciences are impacting us. And I guess both we can learn from the social scientists of how to think about this, but also we need to start thinking of how what we're creating changes the society around us. And I guess this is more the topic of the next panel, but I guess in responding to your question, this is a very important thing that we need to explicitly think about and learn from social scientists on how to think about this.
I guess on this point about the social science, part of the reason why we are here, I believe, is that engineers have been extraordinarily successful, and they have created all these great systems that interact with people who interact with other people, and suddenly now, like human behavior and human interactions have become a topic of something that is computer science, and we in the social sciences, we have been thinking about that for a while. Okay, so I think that we have something to contribute and put on the table.
So we have time for one last question.
Thank you. This is Will Knight from Technology Review. I thought your demonstrations were all fantastic. I especially liked the computational jazz. And one thing that I sort of perceive is that machine learning is having a huge impact on the world of computer science. And it is moving so quickly, and there are all these techniques which are open new possibilities in creativity, things like GANs, and I'm thinking of Project Magenta. So I'm just curious, I know that's part of the vision for the Schwarzman College is to integrate AI. So I'm just curious how you think it's possible to sort of keep on top of that when it's moving so quickly in computer science.
I guess we certainly can start with the theme that came in the end of the opening talk about the lifelong learning. The students realize, given how fast the field is moving, that they're going to have to keep on top of this. They're also very excited about machine learning, both because it's a field that is exciting and new, but also because it gives them an amazing opportunity to go to some company and know something that the senior guys who have worked there for a long time haven't. Like if they go to any of the companies, including the star, Google, Facebook, the senior engineers there didn't take a course on machine learning or didn't take a course on GANs because those things didn't exist when they were students. This makes them super excited. So, again, I can't answer how MIT will integrate this, but I think all computer science departments, whether at MIT or at Cornell, we are creating coursing, we're creating opportunities for our students to learn the basics and to realize that this is a moving field and they're going to have to keep, keeping their eyes open of what's going on.
I think a little more specifically with respect to your question about like what Google Magenta is doing and GANs for generating artwork and things like that. So I see students who get really excited by this, right? This is kind of the cutting edge of what's happening in computation and creation. And they want to dive in and start, I want to build a system that, kind of like what I did in about 5 minutes, but hopefully better. But then you start asking the questions like, well, why are you doing this? And is it legitimate for a computer to make artwork for us? And do we enjoy it? And is the artwork, which is what it's supposed to do, is it bringing up sort of interesting controversial issues or matters of opinion or matters of taste or matters of aesthetics? And so all these new questions that are coming up because of where machine learning is today, I think makes it even more important that we study the humanities just as humanities, and so we have to know how artists think and how to become artists. We have to study music from first principles and actually take the theory classes. We have to take art history classes and sculpture and visual arts, just to have those as a foundation so that we can evaluate what these GANs are creating for us.
So let us thank our panelists.